All right, welcome everyone to 16.8. We're talking about Stokes' theorem. And Stokes' theorem, like we saw in the pre-class video here, is an upgrade of Green's theorem. So rather than being now in the plane, we are in space. So our surface, again, XYZ space. And so the normal vector is not necessarily just K, right? K is, of course, the normal vector for the XY plane. But in general, right, if you're just a surface in space, then your normal vector is probably not K. And so that's why we have dot n here. Now, of course, this C, this curve, that's the boundary curve for our surface, and this S are related together. And so we do have to check using the right-hand rule and whatnot that we're not messing with the orientation. And so this talks a little bit here, right? N is an upward pointing unit normal vector. C is a positively oriented when viewed from above curve. Of course, if you were to swap that around and have like a downward pointing unit vector, then you would want to go clockwise, right? So have a negatively oriented curve when viewed from above. So again, you can always figure this out just using the right-hand rule. And I showcased this a bit in the pre-class video. We'll get more practice, especially in the second class. I try not to go too much into it in this class, but we get 2 days on Stokes' theorem. And so here was an example and just showcasing that no matter which way you choose to evaluate this, either with the surface integral or with a line integral, in both cases, you got the same result. Of course, this was just a result of 0. But yes, it did match. In general, I typically find, right, line integrals are a little bit easier. And so you would think maybe when possible that we'd be swapping, from a surface integral into a line integral. And this is the main way that we'd use this equals. But it actually turns out, and we'll see here, that there are times where you'd want to do kind of either switch here. So let's go ahead and transition and start to look at our new problems for today. So like I've labeled this, right, this is Stokes, the two-way street, right, that really you do sometimes want to trade in a surface integral for a line integral, but we'll see that there are also cases where you want to turn in your line integral for a surface integral. Either way, when a problem says to use Stokes' theorem, you need to trade in what you have for the other side of the equal sign. So in this case, we are trying to evaluate out this surface integral of the curl of f dot ds. And so because of that, we are going to apply Stokes' theorem, curl of f dot ds. And we are going to transform this surface integral into a line integral. If you don't do this, then you haven't used Stokes' theorem. You've just evaluated out this interesting flux integral, the flux of the curl, I suppose, just like we did in 16.7. So you haven't used Stokes' theorem. So using Stokes' theorem is, again, trading in what you have, which in this case, we're interested in calculating out this surface integral for the other side of the equal sign, which in this case is a line integral. All right, so we are using Stokes' theorem. We're trading in our surface integral for a line integral. And now we need to actually evaluate this out. So again, in general, I like line integrals. I think they're easier than surface integrals in general. And so I'm quite happy with this trade. But now we need to think about what is the C thing, right? So I can go ahead and start to write down, for instance, I know what F is. It's XZ, YZ, XY. And this is just given in the statement of the problem. But now I need to figure out what this boundary curve is, because that's the thing that I need to parameterize in order to, right, to figure out this dr, right? I'm going to need to take the derivative of it and all that sort of stuff. So let's go ahead and read the problem fully. We say that S is the part of the sphere that lies inside of the cylinder above the XY plane. So we have a sphere of radius 2. That's this bit. We want only the piece that lies inside of the cylinder. And this cylinder has a radius of 1. It's missing its z component here. So let's draw something like this. Oops. And it lies above the XY plane. And that's good because, right, when I saw this, I thought, okay, well, we have a piece of the sphere up here, but then we also have a piece of the sphere down here that lies inside. But we only want the piece that's above the XY plane. And so if I was to maybe shade this in, it would be this piece up here. So again, my surface is the portion of the sphere. So I'm going to be shading in some portion of the sphere, only the piece that lies inside of the cylinder. So anything outside of the cylinder, not really interested in, and only the piece that lies above the XY plane. So, okay, there's one piece right there. So that's my surface. The boundary curve is going to be, again, where the surface abruptly stops. So that's going to be this curve right here. And we can see that that curve kind of comes from where this cylinder and the sphere meet. So it's this curve of intersection between two surfaces. So I want to know, where does this sphere, x squared plus y squared plus z squared equals 4, where does this meet with x squared plus y squared equals 1, this cylinder? And so, well, I could go ahead and, maybe substitute in everywhere I see an x squared plus y squared, I could put a 1 into my sphere equation. And so this is going to give me 1 plus z squared is equal to 4. So therefore, z squared is 3. So z is going to be plus or minus root 3. So of course, right, there's another place where these things intersect, and that's down here below the xy plane. So that would be the negative root 3. So given the fact that we are above the xy plane, we need to have a positive z value. And so I'm only interested really in the positive here. Okay, so that's the z value, but I still need to know, right, what are my x and y, right? I need a parametrization. So I now know, right, x equals something, y equals something, z equals something. I now know that z is fixed at a constant. It's at a height of root 3. But I still need to parameterize my x's and my y's. And so now, with this fact that z is root 3, I could plug that in into either one of these. Well, I guess really only this first one here has a z. And when I do that, they're both going to give me the equation x squared plus y squared equals 1. So this is going to be a circle of radius 1. I'm going to go ahead and borrow from polar and get 1 cosine t, 1 sine t. Now, if you want to think about the orientation and all that sort of stuff, we can go back to the problem, right? And it doesn't mention a specific orientation. So whenever it doesn't do that, right, we think about a positive orientation. And so this would have a outward or upward orientation for our surface. So our normal vectors would look something like this. And that's going to correspond to a positive orientation when viewed from above, right, on our boundary curve. So therefore, it's going to be parameterized in a counterclockwise when viewed from above. So that's going to be using our regular orientation, right, with a 1 cosine t, 1 sine t, that goes in a counterclockwise direction. So, okay, yes, this is correct. And so if you wanted, right, we could write down r of t is equal to cosine, sine, and root 3. In order to go all the way around the circle, we're going to want t to range from 0 to 2 pi. That gets every point once and only once. And of course, we're about to start plugging that stuff in over here, but we also need r prime. So let's go ahead and calculate that out really quick. So derivative of cosine, negative sine. Derivative of sine, cosine. Derivative of a constant is just 0. All right, so now let's go ahead and plug this stuff in over here. So again, we're going to be doing a t integral. That means we can use our t bounds, 0 to 2 pi. Instead of x, I'm going to put a cosine. Instead of z, I'm going to put a root 3. So that's me just reading off that first coordinate there and swapping in what x and z are in terms of t's. Next up, we need yz. So that's going to be sine of t root 3. And then finally, xy. So that's going to be cosine sine. And we need to dot product this with r prime of t dt. So we're going to have what? Negative sine cosine 0. Running out of room, so I apologize that I've scrunched it up a little bit. Let's go ahead and evaluate out our dot product here. So I'm going to have what? Negative sine cosine root 3 plus sine cosine root 3 and then plus 0. So notice that these are like terms. One's positive and one's negative, so they perfectly cancel out. And so this just becomes the integral of 0. So my final answer here is going to be 0. All right, so hopefully that was a pretty nice start here. And I just wanted to remind everyone, right, that sometimes the difficulty of these problems is identifying the boundary curve, right, of the surface and thinking a little bit about if the parameterization is oriented correctly. And so I would invite you, though, even though, right, this is a difficult bit, if you're on a quiz or an exam, and if you're having a hard time visualizing, if you don't know if it should be going in a clockwise or counterclockwise direction or whatnot, just choose one of them and go with it. Because especially for if it's a standard response style question, you can get the vast majority of points, even if you choose the wrong orientation, right? You may get a couple points taken off, one or two, maybe on like a 10 or 15 point problem, in comparison to if you just kind of start to panic and you don't do anything, you don't write, any of this down, then you're going to get very few points. So choose a parameterization, even if it's the wrong one, and you can always go back and alter it later if need be. Because in order to change the parameterization, excuse me, in order to change the orientation, right, remember that you're just going to be off by a negative sign. So if you orient it positively and go in the counterclockwise direction when viewed from above, let's suppose you get the answer of 5, right? And the answer was supposed to be going in the clockwise direction, right? Then the answer would be -5. So you can always kind of go back and fix that at the end, just with a sentence or two. Say, well, I calculated it out with a positive orientation, but it turns out you should have a negative orientation because the right-hand rule, therefore the final answer is -5 or something like that. So again, the big thing is just don't get paralyzed, because you're afraid you might get it a little bit wrong. Still just do the workout and get as far as you can. All right, so let's go ahead and do another one here. This one's clever, right? Nowhere in this problem does it say use Stokes theorem, right? So we have to decide to use Stokes theorem if we'd like. For this problem here, we can see that our line integral is a square in the YZ plane. If I wanted to go ahead and parameterize this, right, I would really have to parameterize it as 4 different line segments. There's no way to parameterize this entire curve in just like one go. So I'd have to parameterize, this first piece, I'll call it C1, and then the second piece, C2, and then this third piece, C3, and then this fourth piece, C4. And then I need to evaluate out the line integral over each one of these and add up all of those results, and that would give me the overall line integral over this entire curve. So you can see that I would need to do, excuse me, 4 line integrals, and that's a lot of work, right? That takes a while. So this is one of these situations where, in fact, by using Stokes theorem and by swapping this into a surface integral, we'll be able to do this with just one surface integral. So this is what I mean by that Stokes theorem is a two-way street. So even though line integrals are in general nice, right, we'd have to calculate out 4 of these things, and that's going to take a while. Well, if we were to evaluate out the surface integral, we're going to have an easier job of this. So I'm going to choose to apply Stokes theorem, even though this problem doesn't say, hey, you have to use Stokes theorem, just because the other way is going to take forever. So I'm going to swap this in for a surface integral. And the first thing that I need to do is to evaluate out the curl of f. So let's go ahead and spend a little bit of time and calculate out the curl of f. So again, i's, j's, and k's. We're going to have a partial with respect to x, a partial with respect to y, a partial with respect to z. And our vector field is y, z, x. When I take this determinant, I'll have stuff with i's minus stuff with j's plus stuff with k's. Let's go ahead through this, crossing off our first row and first column. Partial derivative with respect to y of x is going to be 0, minus partial derivative with respect to z of z is going to be 1. Next up, moving to our first row and second column, partial derivative with respect to x of x will be 1, minus a partial derivative with respect to z of y, that's going to be 0. And then finally, first row, third column, partial derivative with respect to x of z will be 0, minus partial derivative with respect to y of y is going to be 1. So we're going to end up here with a curl of -1, -1, -1. And so let's go ahead and plug that into my surface integral. So -1, -1, -1. And then remember, we need to dot product this with ds. That right there is notation, right? So notation here, this is going to be dot n ds. where n is supposed to be the normal vector of the surface that has this as the boundary curve, right? Whenever we swapped in from C to S, C is supposed to be the boundary curve for the surface S. And so if I was to go over here and kind of shade in what I think is a reasonable S, and this isn't the only correct answer, but I think it is the nicest one, right? This surface right here has the boundary curve of C. That surface is part of the YZ plane. Of course, the YZ plane goes on forever, but this is a piece of it. Now, the YZ plane, of course, has the equation of x equals 0. So x equals 0, and again, this is just a piece of it. So I need a normal vector to the plane x equals 0, or that is the YZ plane. So you can almost just look at this, and maybe some of you will be completely happy saying that a normal vector is going to be, and of course we want a unit normal vector, is going to be 1, 0, 0. And of course, it could be pointing in the positive x direction, or it could be pointing in the negative x direction, right? So 1, 0, 0 would be a perfectly good way to do this. Of course, right, if you want to think about how do we do this more systematically rather than just looking at the picture, because again, this was a relatively nice one. So you can just look at it and see, oh yeah, 1, 0, 0 will work. That's a unit normal vector, right? 1, 0, 0 would be pointing off in this direction here towards the positive x-axis. And it's a unit vector, right? It has length 1, sure. Or it could be pointing in the opposite direction. But if you wanted a more systematic way, right, a good way to do this is back in our 14.6 method, which says that if you have a function with all of your variables on one side and a constant on the other side, oops, then a way that you get a normal vector is thanks to the gradient. So the gradient is a normal vector. So if I was to look at my equation, notice it almost looks too easy, right? So we have all of our variables on one side, and we have a constant on the other side. If I was to take my gradient, I need to do a partial derivative with respect to x, a partial derivative with respect to y, a partial derivative with respect to z, right? That's going to be a perfectly good normal vector. Now you would still need to make that a unit normal vector, and you need to think about orientation, so there could be the plus and the minus, right? But this would be a perfectly good normal vector. So we get the same result as we had here. So I'm going to go ahead -1, -1, -1, dot. And again, my normal vector, my unit normal vector is going to be 1, 0, 0 or -1, 0, 0. And this is, again, where I was saying that if you're at all hesitant about what your normal vector ought to be, and with the right-hand rule and all that sort of stuff, I would just say, choose one and do it all the way through. And if you need to come back and change it later, that's perfectly fine. But if you just stop here, you're going to be leaving points on the table, right, that you could get otherwise. So let's go ahead back here really quick and think about, right, should this be the positive or the negative? So if I was to use my right-hand rule, so, oops, I didn't mean to erase the purple necessarily. So if I was to use my right-hand rule, and again, my fingers on my right hand need to follow the curve. So when I put my hand up here, I'm trying to get my fingers on my right hand to kind of follow the curve here as it goes around. And when I do that, my thumb seems to be pointing outward. Right? If I was to change the orientation and have it going rather in a clockwise direction rather than a counterclockwise direction, then my thumb would have to point into the screen. So we've had some practice at this before, but just as a reminder, right, this is how the right-hand rule works. And so because my thumb is pointing out of the screen towards the positive x-axis, that means I'm going to want to choose the positive one here. And that's going to be the correct orientation. So again, I'm going to choose the positive one. I'm happy with 1, 0, 0, and I don't want to change that. So when I go ahead and I evaluate out my dot product, I'm going to have -1 ds. I can factor out that -1. And now when you integrate 1 over a surface integral, right, this is just supposed to be surface area. So my surface area, in this case, if I was to go back here, This is a 1 by 1 rectangle, or a square, I suppose, right? So this is a 1 by 1 square. And so therefore, the surface area of this is just going to be, well, the side length squared. And so overall, right, 1 squared will just be 1. So my overall answer, right, for this line integral is that the line integral is equal to -1. Again, it's not saying that the surface area is -1, right? The surface area is 1, but then we need to multiply it by this constant that we saw that we got from evaluating our dot product and all that sort of stuff. So the overall answer is going to be -1 for this problem. And again, remember, these are the same line integrals that we did back in like 16.2. This was stuff that we did really for our midterm exam and whatnot, right? When we calculated out these line integrals first in 16.2, we talked about, right, is the vector field helping or hurting, right? And the fact that we have a negative answer here means that our vector field was hurting, right? It doesn't really want particles to go around in this direction necessarily. All right. That is the end of this problem here. Let's go ahead and move on and try another one. I think this is a good one here that, we've seen a couple of examples. I would recommend maybe pausing the video, trying this one on your own and seeing how far you can get, right? So I would recommend, again, pause the video, see how far you can get, and then come back here when you're ready to peek and get a bit of the results. All right. So on this one here, I've gotten to what I think is a decent place to where I really want to start explaining. So I've kind of stopped right here. Notice, by the way, this problem does not say that you have to use Stokes' theorem. So I think this is one where it would be completely legitimate if you wanted to evaluate out just the line integral. This has a little bit of some hardships when you're doing the evaluation, but it's not crazy. But since we're getting some practice using Stokes' theorem, I decided to go ahead and convert this into a surface integral. And so I've swapped in my line integral for, again, the curl of f dot ds, which means, well, I need to calculate out the curl. So I spent a little bit of time calculating out the curl, and you can see that I got the vector 0, 0, and 1 plus 2y. So that was my curl of f. Now remember, dot ds is just notation. It means that you're dotting with a normal vector from your surface and then doing the regular old surface integral like we did in 16.7. And so I've started to swap in some of that. And this is where we need to think now about our surface. So it talks about the curve here. C is the curve of intersection between the plane, y plus z equals 2, and the cylinder, x squared plus y squared equals 1. And again, going to be oriented in the positive direction, counterclockwise when viewed from above. And so here's my picture that I've drawn here. So the curve of intersection between this cylinder and this plane I've drawn in purple. So, of course, there are many surfaces that may have this as the boundary curve, but I think the simplest one is if you just shade it in. And so if you shade it in, that's going to be a part of this plane, which was y plus z equals 2. So y plus z equals 2. Again, that was over here, given to us. Of course, when we go to evaluate out these surface integrals, we've seen that it's very nice, when you actually have to evaluate these things all the way through, if you have an explicit surface. You can do it with parametrically defined surfaces, but it's a little bit of a pain, right? But if you have an explicit surface, a z equals surface, then it's not too bad. And so I went ahead and I just noted on my picture here that we can make this a z equals surface pretty easily, right? And I could just rearrange and get that z is equal to 2 minus y. So if I'm interested in what is my normal vector, and I have a nice explicitly defined surface here, remember you can get a normal vector for situations like this. And this came back from 14.4 when you were first doing tangent planes and all that sort of stuff. The normal vector for an explicitly defined surface is going to be this plus and minus, what we'll say g sub x, g sub y, and -1, right? So in our case, if I was to go ahead and take my partial derivatives, I'm just doing g's because, right, we've already had maybe a function f that we're well, I guess this was a vector field, so maybe I could have used little f here, but well. So when I start taking partial derivatives, partial derivative with respect to x is going to be 0. Partial derivative with respect to y is going to be -1. And we always have that -1 in our z component. Now, if we want this positively oriented, right, that means that our normal vector here should be upward pointing. So the fact that I have a negative z coordinate here means that this is not upward pointing. So in order to get that, I'm going to go ahead and choose this extra negative sign here and distribute that to each piece. And that's going to give me 0, 1, 1. So now if I was to check again with like the orientation and everything, we said that the curve C should be going around in this counterclockwise direction when viewed from above. And if I take out my right hand and I rotate my fingers around in the direction of this curve, right, we can see that my thumb points in this upward direction. So again, it should be positively oriented there. So my normal vector in this case is going to be, let's go ahead and write all this other stuff. But this is going to be dot 0, 1, 1. And again, we've already thought about the orientation and everything. And again, this is not a unit normal vector here, right? This is not unit. But the nice thing about when we use this explicit form here, we also get to trade in this ds for a dA. So that's the nice thing about using this explicit form for surface integrals, or the parametrically defined version for surface integrals as well, is that you then get to you've swapped out the ds for the dA as well. So now at this point, we need to be integrating over this region in the xy plane, right? We have a dA now instead of a ds. So maybe I'll use r here. And again, that was our surface. So if I was to take this surface and to smush it down into the xy plane, maybe this is the xy plane down here, we're going to have still a nice circle of radius 1 because it's all inside of the cylinder. And so let's go ahead and maybe set up here. When I do my dot product, I'm going to have 1 plus 2y. And again, in the xy plane, looking at it head on, it's going to be all the stuff that's inside of this circle of radius 1. But now I have a double integral to evaluate, right? And I can evaluate this just like I did back in chapter 15. I can either do y first, or I can do x first, or I could decide on polar. So because this is inside of a circle of radius 1, I'm going to decide to use polar in this case. So let's go ahead, start swapping to polar. So I'm going to have 1 plus 2 r sine theta, dr d theta. R's are going to range from 0 to 1. Thetas are going to range from 0 to 2 pi. And I hope that you're yelling at the screen right now, right? Because again, anytime you switch into polar, right, we're going to need our Jacobian. We're going to need this extra r, this extra integration factor. And so don't forget that, even though, right, I know this was brought up a little while ago now, but always remember when you switch into polar, you need r dr d theta. All right. So from here, let's go ahead and start evaluating. So let's see. If I was to distribute this r, this is going to have r plus 2r squared sine theta. And let me go ahead and integrate that here in my next step. So integrating r, I get 1 over 2r squared. And here we're going to have 2/3 r cubed. And we need to evaluate this from r equals 0 to r equals 1. And then we'll still have a theta integral. 1/2 plus 2/3 sine theta. Let's go ahead and integrate this. So we're going to have 1/2 theta minus 2/3 cosine of theta. And this we need to evaluate from 0 to 2 pi. So doing this term by term, let's see, I'm going to have 2 pi minus 0 in my first term. My second term, 2/3, and cosine of 2 pi is going to be 1, and subtracting away cosine of 0 is going to be 1. So actually 1 minus 1, that part's just going to be 0. And so my answer at the end of the day is going to be pi. So my overall result is pi in this case. And I do have a remark here, right, that says that if you didn't want to use Stokes' theorem, again, completely legitimate, you'd have to evaluate out this integral here. And I'd say that the most complicated bit are these first two right here. Again, not impossible by any means. We used to do this all the time in Calculus 2 and whatnot, but it takes a little bit of work. So, All right, and the last thing here is, yeah, the surface that I chose, like I mentioned, not necessarily unique. However, it is the nicest choice. Of course, you could have chosen some crazy surface with this C as your boundary curve, right? You could do some interesting like balloon sort of surface with that C as your boundary curve. So the surface is not unique, but it is the simplest surface. And so, and especially because we have to find the normal vector of that thing, choosing a nice simple surface has some advantage. All right. Well, we got one more to go for today. So let's go ahead and try this one together here. So S is going to be the surface formed by capping the piece of the cylinder here um, with the top half of the sphere. So let's go ahead and, like it mentions here, let's draw this thing. So S has a few pieces. So we have this cylinder. So if I was to draw this, X, Y, Z maybe. So from Z equals 0 to Z equals 4, and actually I'm going to decide to do this in green. So from Z equals 0 to Z equals 4, all the way up here, we're going to be interested in this cylinder, and it's a circular cylinder where the radius is √2. So, okay, fine. Something like that. Again, this would normally go on forever, except for we've said that we have some bounds, and Z ranges from 0 to 4. Okay. And then we also have something on the top, right? With the top half of the sphere, x squared plus y squared plus z minus 4 quantity squared equals 2. So this would be a sphere that is centered at 0, 0, 4. So that's actually, and maybe I'll use purple for this one. So it's going to be up here. And it looks like the radius of that sphere is also √2. So if I was to draw the sphere, we'd have something that looks like this. And again, it's only the top half. All right, so that right there is my surface. And my question is, what is the boundary of S? So remember this notation here, the partial symbol means the boundary of S. So again, the boundary is supposed to be where the surface abruptly stops. And since we've glued this sphere onto the cylinder here, right, they are connected. And so there isn't a place right here where they abruptly stop. The only place where, if I was making this out of paper or something like this, where I'd have to, make a cut or where I really see there's an edge is going to be at the bottom here. I like to think about sometimes the boundary of our surface. If I was an ant walking along the surface, right? Where is a place where I could go from the outside of the surface to the inside of the surface, or vice versa, right? How could I go from the inside to the outside? And I'd have to go through this curve here, right at the top, right? If I was an ant walking along up here or whatnot, there's no way to anywhere near there to go from the outside to the inside, for instance. And likewise, because these are glued together, right? If I was an ant walking along here, right? Again, there's no way to go from the outside of this thing into the inside. All right, so the boundary is there in the XY plane. It's at the bottom of this. And I'd like to parametrize C so that it has a positive orientation. So that's part of this green surface here, which here's my equation. And again, it's supposed to be in the XY plane, which means that Z was equal to 0. So again, the big equations that I'm looking at are x squared plus y squared is equal to 2. And Z was equal to 0 because, again, the boundary was in the XY plane there. So this is the thing that I need to parametrize. And okay, well, again, I'm going to kind of steal from polar coordinates. And I'm going to think about a parameterization where x is equal to √2 cosine t, and y is equal to √2 sine of t, and z is equal to 0, of course, right? It's said here that z was 0. In order to go around once and only once, right, I want t to range from 0 to 2 pi. And if I want to write this in the vector form, right, I could do that as well. All right, so there's a parameterization. Notice that this is going in the classic counterclockwise direction because I've chosen the normal parameterization where x has cosines and y has sines. Again, if you wanted to swap that out, we've talked before about there are many ways to change the orientation. For instance, you could have one of these have a negative sign, and that would go then in the clockwise direction. But this has a positive orientation with respect to the outward normal, and so I'm happy with that. And then the last bit here is to evaluate out a surface integral. Well, it's had us do in these first couple parts, trying to visualize the surface and parameterize a boundary curve. We have a surface integral with a curl of f. It doesn't say that we have to use Stokes' theorem, but because of all of our work beforehand, I would have a pretty easy time swapping this, because again, I've done the work of figuring out what the parameterization is for the boundary curve and all that sort of stuff, into a just regular old line integral. So that's what I'm going to do here. So let's set this up. We know we're going to be doing an integral with respect to t. So that's going to be 0 to 2 pi. Let's see. Everywhere I see a z, I need to put a 0. So that's quite nice. 0 plus x. That's going to be root 2 cosine t. Next up, we have something with a z in it. And plus y. So that's going to be root 2 sine of t. And then finally, our third component is just 0. Okay, so that's quite nice. And then we're going to be dot product that with r prime of t dt. So let's see, I need to take the derivative of this. So I'm going to have what? Negative root 2 sine. And then I'm going to have root 2 cosine. And then I'm going to have, well, the derivative of 0 is just 0. So if I was to go ahead and evaluate out my dot product here, I would have negative 2 sine cosine. So again, here's my first component times my first component. So root 2 and root 2 makes the 2. There's that negative sign, and then, well, there's one sine and one cosine. Next up, we're going to have plus, and root 2 and root 2 make 2. And again, we have a sine and a cosine. And 0 times 0 is 0. And so this is another one where we're going to be integrating just 0 in this case. So my final answer for this problem is 0. All right, well, that is it for today's lesson on Stokes' theorem. Again, we have one more day for Stokes' theorem, so we'll do even more of these sorts of problems. But yeah, try some of the web work homework, see how far you can get on those, and then come and watch the next video and get some more problems kind of under our belt for Stokes' theorem. All right, have a wonderful day. I'll catch you next time.